Welcome back. I have now moved to the right, which should make it easy for you to see the slide. This was the quiz before the break, and of course the answer is easy. It was on a previous slide, and if you don't remember this, just go back and review. Okay, so before the break we had bundles of apples and bananas. We had a utility function that tells us, given how many apples, how many bananas we have, how happy we are. And the next concept we're going to introduce is indifference curves. So when are you indifferent? You are indifferent between bundles if essentially you don't care which bundle you get, right? Since we can change these bundles with very small amounts, we can always find other bundles that make you indifferent. I'll get back to that between a number of bundles. And then we will have an indifference curve, and that is simply a curve that connects all the bundles between which you are indifferent. Okay, some more explanation. So here again we have apple banana space, and suppose that initially I have bundle A with 5 apples and 10 bananas. Now suppose that somebody comes in and takes away 5 bananas from me and asks, well, you now have 5 bananas rather than 10, so how many apples do you need to make you just as well off as you were before, so that you don't care which of the 2 bundles you get? Okay, you think about this for a little while and you conclude that that number is 7.5. So if you have 7.5 apple, 5 bananas, then you're just as well off. Your utility is exactly the same as in the case that you have 5 apples and 10 bananas. So in other words, A and B are on the same indifference curve. You are indifferent between them. I can also do that for 3 bananas, right? I can ask you, well, if you get 3 bananas, how much apples do you need to make you just as well off as before? And if your answer is 10, then C, the resulting bundle, is on the same indifference curve. And here I've drawn that indifference curve, so that's one indifference curve, right? That connects these 3 bundles in this case. Okay, here I have a situation where I have drawn 2 indifference curves. So I'm indifferent between all the bundles on this curve, but I'm also indifferent between all the bundles on this curve. What about this curve? Which curve makes me happier? Which curve gets me high utility? Well, that's easy to think of if you go back to my non-satiation assumption, right? This is 1 point on indifference curve 1. This is 1 point on the indifference curve 2. These 2 points have the same number of bananas, but there are more apples here than there are here. So necessarily, this bundle should make me higher off than that bundle, but all the points on an indifference curve make me indifferent, make me equally happy. So in other words, on this indifference curve, my utility is higher than on that indifference curve, as you can see here. Okay, so if you think of indifference curves, it's good to note the following. What we have here is essentially a 3-dimensional function, right? We have apples on the horizontal axis, on the x-axis. We have bananas on the y-axis, and then on the z-axis we have how much utility that bundle gives us. So essentially we have a 3-dimensional graph, if you like. And having indifference curve is just a way to make it easier to represent that 3-dimensional function. Exactly the same thing happens in the weather report, right? If you have a weather map like this one, then all these points, or this curve rather, connects points with the same air pressure, 1040 millibar in this case. So this is not an indifference curve, but rather an iso bar. But the same concept, you just go to a level of 1040 here, you slice through your curve, and then you get all these points, all points that give you the same air pressure. So the same thing is true with an indifference curve. You also have that with maps that of mountains, right? Then you also have these lines that represent how all the points that at a certain height. So that's the same trick. You have ISO height curves that connect all points with the same height. And indifference curves just like that. It connects the points with the same utility. Okay. So what do we know about indifference curves? Well, first of all, since we are able to compare all bundles, that's completeness, that also implies that we can draw indifference curves. We know the utility, we can tell you how much we like each bundle, so we can draw. I also told you this, non-saturation implies that curves further from the origin represent higher utility. The more you go to the northeast, the happier you are, but you already know that studying in Groningen. This one is a bit more involved. You can show that indifference curves never cross, and that is implied by transitivity. So there's a nice proof for that. And the way we're going to prove that is as follows. We're going to start out with by assuming that it actually is true, and then we derive a contradiction. So first step in the argument, suppose that indifference curves do cross. So that's what I've drawn here. I've drawn two indifference curves that actually cross each other. Why can this not happen? Well, take 2 points, D and F. D and F are on the same indifference curve, so obviously both points should give me the same utility. I should be indifferent between them. Okay, but now take points E and F. These 2 points are also on the same indifference curve, so I should also be indifferent between these 2 points. But wait a minute. Look at points D and E. E has more apples and more bananas. So E should give me higher utility than D. But that cannot be true, since transitivity implies that if I'm indifferent between D and F, and I'm indifferent between E and F, then I should also be indifferent between E and D. But at the same time, I've just shown you that E should give me higher utility than D. So that's a contradiction, right? Through one channel using transitivity, I've shown that E and D should give me the same utility. But then I've shown that due to non-satiation, E should give me higher utility. They cannot both be true. So the thing I started out with, the assumption that indifference curves can cross, that cannot be true. So this leads to a contradiction, which implies that indeed indifference curves cannot cross, because if they would, you would end up with weird contradictions. That's the argument. Okay, so if they cannot cross, they should be parallel, right? Okay, more characteristics. This one is also a bit tricky. They should be convex to the origin, which means that they should have this shape, and that is implied by diminishing marginal utility. Let me try to explain that. Here I have an indifference curve, and this indifference curve is indeed convex to the origin. If I'm here, now let me start it differently. Suppose that I'm in point A, then I don't have that many apples, so I'm actually willing to give up quite a few bananas in order to get an extra apple. In point B, however, I already have quite a few apples, so I'm not willing to give up that many bananas in order to gain more apples. So that's just my diminishing marginal utility, right? So what that implies is that I have few apples. I'm willing to give up many bananas. If I have many apples, I'm willing to give up only a few bananas to get extra apple. So in other words, up here, the curve should be steeper than down there. And that implies that it should have this general shape, right? It should be convex to the origin. Point C even more so. And the explanation that I just gave is also on the slide here. As you get less bananas and more apples, you want more extra apples in order to be willing to give up a banana. Or vice versa. And therefore they are convex to the origin, these indifference curves. So they're always shaped like that. So we know quite a few things. Without making too many assumptions, we already know quite a few things about our indifference curves, right? They're parallel, they're convex to the origin. I already argued this essentially. Indifference curves describe trade-offs. They tell you how much of one good you are willing to give up for more unit of the other good, and the slope of the indifference curve captures this trade-off. We saw all of that on the previous slide. So it's good to have a sort of measure of that, and we call that the marginal rate of substitution. So that's the rate at which you're willing to give up one product in order to get more of the other product. So how along the indifference curve, how many delta B should I give up to get extra A? How many bananas do I have to give up to get extra apples, or vice versa? And the minus in front here is just to make sure that we end up with a positive number, because that's always easier to play around with. So this marginal rate of substitution describes the rate at which one is willing to trade A for B and be equally well off, since we are on the same indifference curve. Okay, so here's another example with socks and t-shirts. Here we have an indifference curve. Here the slope is -2. So I'm willing to give up 2 t-shirts for 1 pair of socks. So that's my margin rate of substitution at this point. Here it's -0.5, the slope. So my MRS is 0.5. I'm willing to give up half a t-shirt to get 1 more pair of socks. And if I move down this indifference curve, I have a diminishing marginal rate of substitution, as you can see here. Okay, so if we look at this point, here's an interesting derivation. So what's my marginal rate of substitution? That's the change in y divided by the change in x. That gets me on the same indifference curve, and that was equal to 2 at point A. So that means that what happens to your total utility? Well, if you give up a certain number of socks and you get a certain amount of extra t-shirts, what happens to your utility? Well, at the margin, every extra pair of socks, by definition, gives you the marginal utility of socks, right? And every extra t-shirt gives you, by definition, the marginal utility of t-shirts. So if I get delta Q socks extra socks, then this will be the effect on my utility. And for t-shirts, this will be the effect on my utility. But if I stick along this indifference curve, then the total change in my utility should be 0, right? I stay on my indifference curve, so my utility doesn't change. So the total change in my utility, I just figured out that the total change equals this expression here, but the total change should be 0 since I just stay on my indifference curve. Okay, but that's nice, because that means that I can just rearrange this equation. I can write it like this. I throw the socks to the other side, so that gives me this equality. And if I then divide everything by Q socks and MU t-shirts, I can also rewrite this equation to look like this. And if you cannot follow this right away, just review it, look at it again, and if you still don't understand it, live with the implications. You may still be able to pass this course without understanding this, but it would be very useful if you do. Because on the left-hand side, I have something interesting. On the left-hand side, I had exactly my marginal rate of substitution, right? So what this implies is that I can just write my marginal rate of substitution as the marginal utility of socks, in this case, over the marginal utility of t-shirts. So that gives me the slope of my indifference curve. If I know my utility function, then this is a simple way to calculate the slope of my indifference curve. And that's again repeated here. So my marginal rate of substitution, change in one product divided by change in the other product, and that equals the marginal utility of socks over that t-shirt. Small side steps. Here are a couple of special types of indifference curves. So suppose that you consume two different products, 1 liter bottles of cola and 2 liter bottles of cola. Doesn't sound like a very particularly healthy diet, but assume that this is the case. Okay, in this case you would have a rather special indifference curve, right? Because you don't really care how many 1 liter or 2 liter bottles you consume. You only care about the amount of cola that you get. So any 2 liter bottle is just as good for you as 2 1 liter bottles. So in other words, your indifference curve is going to be straight line. 8 liters of cola is just as good for you as 4 2 liters, and every combination in between as well, and the same for the other levels of utility. So in that case, you would have a straight line, and in that case, your products are perfect substitutes, as we call it. So with perfect substitutes, your MRS is constant, as you can see here, right? So that's a special case. Here's another special case. Suppose that I have left shoes and right shoes. To be able to walk, I need 1 left shoe and 1 right shoe. If I have 2 right shoes, that's completely useless. If I have 2 left shoes, that's completely useless. If I have 1 left shoe and 2 right shoes, then the second right shoe is useless as well. In other words, my utility is only determined by the minimum of the two, right? If I have 12 left shoes and 14 right shoes, then I have 12 pairs of shoes, and I can just throw out the additional right shoes. So that would give rise to indifference curves that look like this. Weird L-shaped ones. Because again, 2 left shoes and 2 right shoes make you just as happy as 3 left shoes and 2 right shoes, since the third left shoe is useless. And if I keep increasing the number of left shoes, that's completely useless, since I still only have 2 pairs. However, if you give me 1 extra left shoe and 1 extra right shoe, I move from A to C, and that would make me happier. So you can only consume the products in combination, and that makes them perfect complements. They must be consumed in a fixed proportion. Which brings us to the quiz of section 4.2. And this already builds on or introduces what we're going to do next, namely to play around with it, to do some calculations. But for now, assume that you have 4 apples and 5 bananas. Your utility function is simply A times B, the number of apples multiplied by the number of bananas. Then what is your marginal rate of substitution? The answer will follow after the break.